Hi, welcome back to my channel, and in this video we're going to learn about normalization of the wave function. So what is normalization of the wave function? But let's recap a little bit and what we have finished. We have finished about Schrödinger equation, and from Schrödinger equation we get this wave function, and from wave function we can get this probability density function. And then we learned about the interpretation of quantum mechanics and wave function collapse and all those things, but we get the probability density function from the wave function. But probability itself has to follow some rules, and this is one of them, called normalization of a wave function. And let's see how this applies in quantum mechanics. Okay, so we have this probability density function from the wave function. We have and so one of the condition this probability density function need to follow is this: integrate from minus infinity to infinity. Then you should get this wave function. This integration should be equal to 1, and this is what known as normalization. All this is a probability density function need to follow this, otherwise it's not really a probability density function anymore, because the particle need to be somewhere, and if this is not equal to 1, then that goes away and your theory doesn't make sense. But we learned about that the wave function collapse, and the wave function collapsed, and then it evolved according to the Schrödinger equation, different from what we have seen before. So one thing you can think about is you can't just keep imposing this condition. What I mean that if the wave function collapses and it evolves, you just can't keep normalizing this probability density. This if nature is really giving us this probability density function, then nature should normalize it. The solution we get is this psi of x of t, but if psi of xt is the solution, then so is a times this psi of x is the solution, and this is what help us to normalize this wave function, because to normalize this wave function we just need to find a that make this integration is equal to 1. And this is what is known as normalization of wave function. You need to find this a. You need to find this a to normalize this wave function, so you get actual probability density. But some of the wave function does not converge to 1. Some of them diverges. So you can't normalize the solution, because if they diverges, they don't really represent probability density. And if also a phi is equal to 0, also not a normalizable function, so non-renormalizable solution doesn't represent physical state of the particle, and you must reject these. And but one of the other thing you need to think about is how do we make sure this normalizing stays as 5 evolve with time. One of the thing we learn about that the wave function, when you make a measurement, the wave function collapses and it evolves according to the Schrödinger equation, different but with a different distribution that was before. But one thing to notice, that does the normalization stay, or do we have to normalize it again? Because if you have to normalize it again, that is a big problem, because you can't just keep normalizing wave function every time you make a measurement, and this is gonna be tedious and would make your theory crazy, and it will make you crazy. And the answer is you don't have to, because once you normalize the wave function and then stays normalized, it does normalization does not change with time. And this is what we're gonna see in the next video. We're gonna see a proof that the normalization doesn't evolve with time, so you are happy, so you don't have to keep normalizing the wave function over and over again. So yeah, so this is the normalization of the wave function. So I hope you like this video. If you do, give it a thumbs up, and I will see you next time. Subscribe, like, and share.